Okay, so in this video we're going to look at the Rutherford experiment and how he discovered the nucleus of an atom and the kind of observations he made, and then we're going to lead on to the other types of particles that are out there from that point on. So we're going to look at all the kind of subatomic particles in this video, maybe over 2 videos. We'll see how it goes. So first of all, Rutherford's experiment. Well, very simply, well, I say simply, but it was a little bit more complex than this, but we're going to simplify it for you here. He basically shot some alpha particles at a thin piece of gold, hence he was firing them at gold nuclei. So here's your piece of gold here. And effectively what he did is he put detectors all the way around to detect where those alpha particles were going after these alpha particles interacted with the gold here. So he had a set of sensors all the way around. And as you'd expect, or as he expected, most of the particles went straight through, undeviated, and through the other side. And the detector here picked up most of the particles. Now, some of them did something strange. They actually deviated off to the side, like this. But this is 1 in every couple of thousand, so, you know, it's not very many at all. But some of them did something even stranger. They did this. And they even bounced directly backwards from where they came. So we have the idea that we have most of them went straight through, few of them were deviated, and fewer still, very few, bounced back at angles of more than 90 degrees to the where the alpha particles were traveling. So this led to a number of really interesting observations by Rutherford. Obviously, he observed that most were going straight through, few were being deflected slightly, and very few were being bounced directly backwards. Now that meant made for quite a lot of interesting observations. So as a result of the fact that these particles are going straight through, it means that most of the mass of the atom is concentrated at the center, incredibly dense, and that the rest of the atom is effectively a vacuum. Because most of the particles were passing straight through. So what could he tell about this center of the atom then? Obviously it was very dense, and that most of the atom was a vacuum, lots of just space. So we had this really dense center of the atom, which we now know as the nucleus. But he also could tell something very interesting about that nucleus, that because the nucleus was incredibly small, that the size of the nucleus was small because of the amount of deflections that actually occurred. So small nucleus. So the center being all in the center, very, very dense, also very small, and the size idea comes from the fact that very few are deflected, and the idea that the particles coming along are only going to be deflected if they get close enough to this nucleus, this center of the atom, which is incredibly small. So this deflection, we can obviously then come to the conclusion that this deflection is happening because of what? Well, we know that deflection happens in the world because of things being oppositely charged. And we're aware that alpha particles are positive. So what does that mean about these really, really small nuclei? Well, it means that they are also positively charged. Because they're repelling a positive particle. So we've got the ideas here that mostly space because of the amounts that just go straight through. It's a very, very small volume, the nucleus, very dense, because most of the mass must be located somewhere, and if it's not everywhere, then it's got to be in a very small point, as it is explained here. And it's got to be positive as well, because it's going to reflect the positively charged helium nuclei, i.e. alpha particles that we have here. So that is kind of the overview, a very brief overview of how Rutherford scattering works. And I'd just like to draw you a picture of that kind of zoomed in, so that you can see that happening a bit more in terms of the interaction between the particles. So here we've got the alpha particle coming in again, but this time I'm going to draw my gold nucleus. We've zoomed in on that gold foil, so here's my gold nucleus, AU. And so what that's going to do is we're going to observe those deflections. So if we have our particles coming in here, only particles that come close enough to the nucleus get deflected. So particles over here are just going to go straight through. However, a particle that gets closer might do something like this. Because it's gotten too close to the nucleus, the alpha particle has been repelled and shot off in that direction. Even fewer still that get too close to that nucleus will bounce off in that direction there. So we get those very heavily deflected alpha particles. And even fewer still go straight in and come straight back out. Now, actually, this distance here is actually an important distance. We actually call this distance the closest approach. Now, the closest approach is a really interesting calculation that you'll do with me in lesson. It works on the fact that the alpha particle has an amount of energy based on how fast it's moving. So if it has an amount of energy, so we can even say energy, that energy can be used to suggest how close it's going to get to the gold nucleus. Think of this closest approach idea as more of a throwing a ball in the air. You don't have a problem with me turning around and saying, okay, well, if I throw a ball in the air, how high it gets is dependent on the kinetic energy it's got. Because the more kinetic energy, the higher the ball's going to get. It's going to transfer that into GPE. We've studied this before. And then eventually, that ball is going to fall back down to Earth, as you'd expect. Well, the situation here is actually exactly the same, just horizontal. And instead of something pulling the ball back down, there's something pushing the ball away. So in this case, we have Earth pulling the ball in that direction, whereas in this situation, we have the gold nucleus pushing the alpha particle in that direction. Hopefully you can see how there's a similarity between these two things. So as a result, we can use very, very similar kind of ideas to work out just how close these get. And have a look back at your Fields equations, because we are going to utilize the equations 1/2 mv squared, okay, the energy of this particle, kinetic energy. And we're also going to utilize an energy equation that you might not have seen yet and that we'll see as part of the more advanced field section of the course, which is about gravitation or potential energy being KQ over R. So this is an equation that you will not have come across yet. but we are going to utilize it as kind of an introduction to fields later on as well. But it's just nice to see how this closest approach works, and actually, hopefully those of you who are more savvy will see what this value is from these equations, and you'll be able to see where these values could come from. Charge, and R, that's your closest approach. So the idea here is that we can utilize some very common equations to help us work out something that's very interesting. And actually, this is what Rutherford did to work out a max size of the nucleus, which, as we now know, is around 10 to the minus 15 meters. Okay, talking femtometers. So that is a very important point to make and something that we should bear in mind. Now, okay, we'll stop there for this video because that's gone on long enough, and we're going to have a look in the next video at looking inside the nucleus, at what's in there, and some other subatomic particles that make up the nucleus.